All right. Hello, everyone. Welcome to yet another academic seminar with Yuki-mas. Thank you all for coming today. We are recording this, so if you want to look back on it, you are more than welcome to. Today we have a really interesting talk on UAVs and using sound source localization. It's going to be presented by Dr. Aimee Zhang. She's a lecturer at the School of Electrical Engineering and Computer Science, and also Yifei, who is currently doing his PhD under Aimee's supervision. So I'll just let them do a quick introduction and let's start going on.
Thanks. Okay, thanks for the introduction. I'll get things started. So hello, everyone. Welcome to this seminar. Today, me and my student Yifei will basically trying to discuss a topic which connections. Okay, so trying to make the drone capability of listening. So if we think about a robot or drone as example, so it doesn't have a ear, right? So by default, it doesn't have a ear. But then if we put a microphone on top of the robot or drone, then it have a ear. But then that means if you have a microphone, then you will be able to make the robot or drone listen. Let's see what is the problem and then how we're going to address the problem. Okay, this connectivity is a bit very bad. Okay, so before the discussion, I will first introduce myself first. I'm currently a lecturer in EECS, UQ. That's how everyone know me, probably from some courses. I'm teaching CS610 embedded systems. I'm also teaching some second year electronic course such as 2400 and then 2004. Yeah, relevant, sounds like. And before that, I was a lecturer in the University of Southampton in the UK. And then even before that, I was in ANU, Australian National University. So I did my PhD, postdoc, and research fellow position there. And now I'm still keeping an honorary position with ANU. Okay. And then back to where I started. I started my degree, first degree in China. And when I started, I'm actually nothing to do with audio. I'm actually more in the automation, test, and control domain. So I kind of build embedded systems for automation and tests and controls. That's my bachelor and master degree. And of course, starting from my PhDs, I get into the area which is the audio signal processing. So now I'm kind of mainly working on audio signal processing, but still get my embedded system going on the way. So sometimes I'm going to supervise students to make embedded audio systems. So going into a bit more about my research, generally my research is in spatial audio signal processing. So when we say spatial audio, it sounds like what means by spatial audio. So generally, if you think about sound, it's generally coming from a particular sound source or multiple sound sources, right? If I'm speaking, I'm the sound source. And maybe if another audience is making a noise at the chair, so there will be another sound source, right, at the same time. Therefore, the sound source propagate to your ear. You can hear the sound, right? That's simple. But then, does that means your ear only hear what I'm talking? No, it's actually reflecting back from the room, ceilings, floors, and everything, right? So there is some kind of scattering and reflecting and everything. So that everything add together, this acoustic scene, the environment, plus what I'm talking, and propagate to your ear, that's the final result you are listening to. And when I say spatial audio, we're trying to see, is there any way we can capture this sound with the information of the original sound sources and also all the environment around you, and whether you can actually reproduce that signal back. And in between, potentially you might need to do some processing and then control the signals, depends on what kind of applications. So like I said, if you capture the sound, if you want to capture the three-dimensional sound, at least you need two microphones, right? So you want to use the difference between the microphones recordings to get the spatial information. Therefore, you could actually have the sound microphones at this figure A, which is the human shape. You have microphone in the ear. And of course, plus your head shape, your torso, your bodies, you can mimic how a real person is listening sounds like. You could also have embedded systems which can be attached to the middle one, right? All these middle ones are embedded systems, so you can attach to the robot. And later on, you will see that some of my application, my discussion today is going to use the embedded microphone arrays to capture the sound. And you could also, if you want to deal with some kind of three-dimensional signals, you could also use microphones on a three-dimensional shape. For example, if you have 4 capsules, you could actually place them in a tetrahedron shape, and the other one, if you have 32 microphones unit on the ball shape, it kind of spherical array. And at the bottom, it's the ones which we use for the reproduction. So like I mentioned, we do some recordings, which want to do some processing, depends on the application, and we want to play the back. So the playback systems can be through headphones. The first one is headphone. It could be also VR devices, so some speakers on VR devices. The second one is an array of loudspeakers. So the second one particularly is a linear shape. And it can be also come with a circular shape. And also at the end, the final one, figure D, is a spherical shape, like a half sphere. So these are the tools which we play with. We do have some of them in our audio lab in UQ as well. So in terms of the applications, the number one application which I'm looking at is the noise control application. So I'm trying to see if I can create an environment and then with some speakers and microphones without using headphones. And the other one is this drone application, which we're looking at the human and robot sound interaction. And also another application which I'm looking at is spatial audio solution for the virtual reality applications. So today I'm going to only focusing on the second one, but if any of you have any general interest for the other topics, feel free to send me emails and we can have a chat. So going to the actual content today, we're talking about the drone audio stuff, right? So remember what we discussed at the beginning. Is there, if we actually adding microphones on the drone, is that done? Is that just getting the recording and then it can be used? That's a general question asking here, right? So now before we talk about microphones on the drone, we're looking at how drone has been used in this sensing application. So existing drone-based sensing are mostly used by using cameras, right? More like a visual information, or using the LiDAR information, like LiDAR sensors. The visual is the majority of the people talking about using in the drone, but very less on the audio. And why need it, right? If you can see from the cameras, do we still need to listen to? We need, because for some applications, especially for the application in the right-hand side, if you have a very dense forest with some kind of fog, if you have a bushfire, so you actually block the vision, right? Some of the vision is not reliable anymore. And in that situation, you actually can rely on the audio information, because audio can actually, doesn't matter with the fogs, right? It can also go through the opticals, right? So these are the benefits. And if you can listen to it, you don't need to see the object. You can actually listen to the sound source from a very far distance and then detect there is a humans or there is some species, which is something you might want to do the rescue for. So therefore, it can be applied for first response service, search and rescue, for example, or like urban planning, or even the industry inspections, these kind of applications. In many cases, if you think about these days, people are making videos based on drones, right? So the drone can carry a camera, but then it can go there and then to make videos. But then most likely the sound you are listening to is it's the manually added sound. The creator actually do it at the end. If you can listen to the original sound, say for example, you are sending a drone to go close to waterfalls, and what you want to listen is the waterfall sound, right? If that can be done, then it's also very helpful. So that can be used in this media applications, recreation applications, and so on. So that's why this having a drone and make a drone be able to listen is important. So what's the challenge here? So we can definitely have a microphones. So now you can see that I'm wearing 2 microphones in my, on my shirt, and I can be able to capture the sound, and also your streaming channel can hear it perfectly. That's because this room is quiet. Generally, there's not much noise in this environment. However, for UAVs, if you place a microphone on a UAV, then the scenario becomes very challenging. Why is that? Because if you look at the distance between your microphone on the UAV and actual sound sources on the ground, this distance could be large, right? It could be 10 meters or even more. But then the UAV rotating, if any of you have played with UAV before, you know that UAV itself is very loud. So it's kind of very noisy. And the distance between that propellers and rotors on the UAV with your microphone, this distance are much shorter, much shorter than the distance from your target sound source to your UAV. So that's the major problem. To give you an impression, I just want to play the sound and give you some feeling about if there is no UAV noise, if there is no rotating noise, or rotor noise coming original from a UAV, just because there is a distance. So if I play a speech signal from the loudspeakers that are on the ground, and what we'll listen to, what will be recorded on the drones.
To the Hebrews, it was a token that there would be no more universal floods.
Okay, it's a weak, but then it's still auditable, right? You can still understand what's the speech. But then here, what we have, the real situation is there's a drone there. The drone is rotating, drone is flying, and that will make something very difficult. So after adding the drone noise, plus this original speech noise, what we really end up with is this. Okay, so if you hear it very carefully, you still can hear some kind of a speech hidden somewhere. But then you definitely cannot tell what exactly is the word, right? So that's a challenging problem. The very bad signal to noise ratio, here we say signal means the target signal. Particularly, we're looking at speech signal or some kind of bird signal or some useful signal we want to capture. And the noise is the drone noise, like the rotating noise, also from the rotors and propellers. So this signal to noise ratio is very bad. It's normally in the range of -10 dB to -30 dB. So I can already show examples. And in this very extreme situation, we can't hear what we want to hear, right? It's still, we didn't achieve make drone listen. So then how to achieve it?
To the Hebrews, it was a token.
Okay. So here, I will generally skip the first applications and then directly jumping into the solution here. So we say, following the story here, we want to listen to what we want to listen, right? But then in many cases, we don't know where is the sound source, right? Like I said, in the searching and rescue scenario, we send a drone there. We don't know where is the survivors. We just don't know where is the human, right? We want to find it and then listen to it and see what's going on, whether we can help them. So then the problem breaks down to the following challenge. Without knowing exactly where is the sound source, then how can we just use the microphones, just purely the recordings, to enhance the speech and listen to it and understand it? So that's the the problem we are answering in this section. So generally, for this particular application, the challenging part is the drone noise, right? So we have already discussed that already. So then, if the drone noise present, then is there any way we can enhance the speech? We have proposed several iterations of the work. So one of the stream of work we have been doing is using a pure signal processing method with some statistics analysis of the drone noise combination then to solve this problem. So here we call it MWF-GMM. So what it means is there are two steps in the solution. The first step, we want to use a Wiener filter, which is a filtering process, to generally remove the noise signal from the raw recordings. So here, in order to remove the noise signals, we don't use one microphone, two microphones. We actually use an array of microphones. So what we're actually doing is we have, this is the array we are using. So we have actually create a, we have actually create an array. Basically, we have one unit which have two microphones, right? This little red one is the actual microphone capsule or unit. And then we have placed multiple of them on the different places on the drone, above, below, on the landing gear, at different places. So you have, if you have 10 of them, you have 20 signals overall, right? And then you combine the information and processing the whole information together. We call it multi-channel filtering process. So with this kind of processing, we end up with a cleaner version of the signal. So from the original capturing, which is the sound, this piece, if we have like a Q number of the microphones, then you get Q number of Ps, right, which is the recording on the left-hand side. And we do this filtering process, apply a filter to it, and then the output, the voice, will be a much better situation. The noise has been much reduced. I'll show some examples later. And then after that, we do another process for further cleaning the noise. So the further processing is another filtering process. We call it Gaussian mixture model Wiener filter. So the second filtering process is done on the individual signals. So after you get this Q number of Ys, basically the output from your first filter, which is the combination of the multi-channel Wiener filter, then you do an individual filter process for each of the channels, and then you will come up with the final solution of the S. And in the second stage, what we do is we actually model the noise signal with Gaussian mixtures, and use that information we basically pre-trained at the beginning to achieve the second cleaning stage. So that's the general idea. Let's see how it works. So first of all, let's listen to the raw recordings. This is the mixture of the noise and the speech. And then after the first stage of the multi-channel filtering process,
the Greeks used to imagine that it was a sign from the gods to foretell war or heavy rain.
so we can pick up the sound.
It was a sign from the gods to foretell war or heavy rain.
But still, there is some kind of a remaining noise where it exists. You can see that even from the spectrogram, there will be some kind of lines in the middle, which remaining noise. And then the final output.
The Greeks used to imagine that it was a sign from the gods to foretell war or heavy rain.
So this is after the second cleaning.
It was a sign from the gods to foretell war or heavy rain.
So you can see that after the second stage of cleaning, the Gaussian mixture model cleaning, we actually can achieve an even better enhancement, right? And if I looking at another way of analyzing this data, so the first figure on the left-hand side is looking at the performance over before and after, right? So the before means just getting the purely noisy signal and just plot the intelligibility and then the speech qualities, right? As we can tell, it must be very bad. So that's the green the blue curve. And then after our cleaning, especially our first cleaning, so the first stage of the multi-channel cleaning, filtering cleaning, then it's reached the red curve. You can see it's significant better than the mixture. And going from the stage 1, the multi-channel stage filtering, to the second stage, which is the Gaussian mixture model cleaning, then the second figure on the right-hand side showing that in the lower SNR scenario, which means at certain scenario when the mixture signal, there's a very noisy situation, then having the second stage actually increase, right, from the dashed line to the solid line. So actually there is a big increase. So you can see that from here to here, there is a big increase. However, if you're looking at the situation where probably it's not that bad, right? So when the SNR level is -10, then having this extra cleaning doesn't necessarily give you a better results. It might give you a similar results or than the first stage results. So which means that depending on your actual applications, depending on how bad situation it is, this kind of two-stage process, the multi-channel filtering plus the GMM filtering, these two processes, it specifically works when the noise level is huge, like the very low SNR levels. And another result we can show in here is bio application. So here we want to record the bird sound. Of course, the original bird sound is like this. While you record it on the UAV, the mixture becomes like this. So if you only apply the first stage of the process using the multi-channel filtering process, somehow it's been cleaned, but not very accurately. So you can see the spectrogram remaining. There is a lot of kind of dense noise, right, in the spectrogram. And for the final results after the two process, so the bird is much more clear now, right? So that's the overall performance we actually have discussed with this proposed algorithm using this two-stage process. And then another angle to looking at this is how good it is to preserve the spatial cues. What do you mean by spatial cues? Like if the original 10 channels have a particular, because all the, so for the same sound source, right, the receiver will receive the sound differently because they are located at the different positions, right? Because the signal will have different delay and decays. So that kind of information will help us to locate where is the sound source. Of course, if there is no noise, then this kind of localization of finding the sound source is easy. But then for this noisy environment, this noisy UAV application, most likely we want to do some cleaning before we actually doing the localization. It's not 100% you need to do that, but I think many cases we want to clean it a bit and then to do the finding the sources, like the localizations afterwards. So therefore, we want to see if that still is possible. We don't want this cleaning stage destroy the whole information of the original multi-channel signals. Therefore, we evaluate how good is this particular process of cleaning the data, preserve the original spatial information so that we can do some other downstream tasks, for example, finding the sources. And then this is another work following the original enhancement work, which is looking at how to evaluate this spatial cue preservation. And we propose a matrix, we call it Hermitian angle. I'm not going into the detail. Basically, this particular evaluation matrix will tell how good it is with spatial preservation before the cleaning and after the cleaning. Basically, we want to preserve that spatial information. So the results showing that we do the evaluation using this method for the proposed method we just discussed, and we find that up until to 6 kilohertz, so the frequency go less than 6 kilohertz, you do get a pretty good preservations. You can see that this y-axis, the lower the better, right? Among the, beyond the 6 kilohertz, it get pretty bad situation. But remember at the very beginning, we said we are targeting speech. So therefore, speech signal is generally less than 4 kilohertz. So this 6 kilohertz boundary is good enough for us for these particular applications. Next, so the discussion we had so far is around signal processing method, right? So we want to clean the signals by some kind of a signal processing method, and then to evaluate how good it is in terms of the speech qualities, in terms of how the preservation of the spatial cues, and so on. So now we want to, recently as machine learning has been well involved in different applications, we're also looking at, is there any way we can potentially improve the results by using a deep learning method? So this is Yifei's work. So he have done a master project or master thesis on this particular application, and then the next time, the rest of the maybe 15 minutes, we'll go over to Yifei and discuss his project.
Yes. Okay. Okay, so hello everyone, my name is Yifei, and I'm a first-year PhD student from the School of Electrical Engineering and Computer Science, and I've been working with Aimee for more than 1 year during my master project, which is to use a deep learning method to achieve a multi-channel speech enhancement for the UAV recording scenario. And so the reason we try to use the deep learning method to do this is not only that I'm from a data science background, so the machine learning method is the only thing that I can do, but also because machine learning method is it have a very complex algorithm, so we can keep as much, we can try to preserve the intelligibility of the speech quality so that we can understand what the content of the speech after we enhance it. So we start from an existing method called the ViewNet. So the ViewNet is originally not designed for speech enhancement or audio denoising, but it's designed for source separation in a song. Like it can separate the human voice and the instrument sound in a song, so that you can sing along with the instrument only part when you go to a karaoke. And so the ViewNet is a typical U-shaped encoder-decoder structure. So it has a series of downsampling blocks and a series of upsampling blocks. And by this particular design, when in each downsampling block, there's a downsampling block that the model basically just downsample the audio feature by 2 in each downsampling block. So with the same size of the convolution kernel, it can see a longer and longer part of the audio feature. In this way, the model can analyze both the local detail and the long-term relationship all in once. And the upsampling blocks simply just upsample the audio feature map by 2 to gradually reconstruct the target signal we want. So if you think about it, sound source separation is actually the same task we want as in the denoising task, because what we want to do is basically to separate the noise part and the target part we want, and we just drop the noise part because the target part is the only thing we want, right? So the WaveUNet has been widely used as a baseline system in many audio enhancement tasks because it works pretty good in daily denoising tasks. But the problem with it is that for the upsampling operation, it simply uses the linear interpolation to do it, which means that it only interpolates a value in the middle of the 2 samples for the feature map and then process it with a 1D convolution. This operation, if you think about it, this is actually a smoothing operation that gradually you can get a recovered target signal, but you lose a lot of details in it. For a daily denoising task, this is okay because the target signal is still the dominant part of the audio input signal. But in the UAV task, the noise part became the dominant part of the audio segment, and we can't bear to lose any detail, which will significantly damage the intelligibility of the recovered signal. That's why we try to seek a different approach to the downsampling and the upsampling in the model. So with the input signal, the first thing we are trying to do is to separate it into even and odd samples. And if we are using the original method I mentioned in the WaveUNet, we simply just flip the finger and then half of the samples disappear. But that's not what we want. And we looked into the discrete wavelet transform, which firstly, it used the even samples to predict odd samples. And with the predicted odd samples and the real odd samples, we can get a predict error, which can be considered as a detail component in the original feature map. And then we use the even samples and the predict error, which is a detail component. We can get the approximation component with the update operation. So that's what the discrete wavelet transform is trying to do. It tries to separate the audio signal into a detail component and an approximation component. So the good thing about this is that once we have the approximation component and detail component, and with the same operator, update and predict operators, we can actually recover the input signal we have. So with the interpolation-based method, you can't do it because it's not inversible. So this way, we can keep the detailed information we need to recover the audio segment. So we replace the interpolation, the downsampling and upsampling block with the lifting decomposition and lifting reconstruction. So here basically is what I just showed. Like we use the predict operator and update operator to decompose the signal into approximation and detail components. And then in the lifting reconstruction, we simply use the same operators from the corresponding decoder, and then we do an inverse operation to recover the reconstructed audio segment. And this way, we can keep the details. And furthermore, here we analyze the two ways of doing the prediction and update. So the traditional method is just to get the mean value of the all samples, even samples, to be the predicted all samples, and get the error value and everything else. But we also consider an alternative method, which is to use the 1D convolution to do the predict and update, which makes the two operations learnable. Like it can be a data-driven training process in the whole model. So based on this, one of the other things is very important in deep learning method is the training process. So here, the original method use only the MSE loss to train the model, which is to compare the sample level of fidelity between the target signal and the enhanced signal. But here, like I mentioned before, in the very low signal to noise ratio scenario, like the drone recording situation, what we want to do is that we not only we want to reduce the noise, but we also want to keep the target as more as possible, so that we can have a better intelligibility. And if you consider this, like if you can perfectly reduce all the noise in the audio segment, but after the enhancement, you still can't understand what the speech is talking about. There's no point of doing this. So we further separate the optimate objection into two. One of them is the fidelity, the MSE loss as before, but we also add a ESTOI loss, which controls the intelligibility of the enhanced signal. And after this, because if you ever train the model, you will see that for different loss functions, they have a very different value range. And if we train with two loss functions altogether, and if one of them have a very large value range and the other one have a very small one, so the one with larger value will dominate the gradient. So the model will only train through one direction, but very small steps on the other direction. That's not what we want. So a very easy solution is to add a fixed weight to each of them. So for example, if we have very large value range for the ESTOI loss, we can simply add a very small weight for it, and then add a very large weight value for the MSE loss. That could be a solution. But one thing is that during the training, the two losses, they can have a very different speed of convergence. So even if we put a fixed weight on each of them, during the training, one of them could be converged really fast, which means the value of it could be getting very small in a fast way. But the other loss function still have a very large value range. So that's why we borrowed a online exponential moving average normalization here to normalize each of the loss functions during the training. So you can take the value from the local steps, like a few steps from the current step, and to estimate the current value range of this loss function, and to do a normalization for each of them. So this way, none of them will dominate the progress. And okay, here comes the experiment. So we use a data set recorded with a real drone with 7 microphones on it, but in the training programs, we only use 5 microphones because the 5 microphones of the same type. And we put the target speaker on different positions, like in different distance and different loudness levels and different angles, so we can have a data set that covers pretty much to avoid overfitting. And okay, here comes the result. So the first one I'm going to play is the original target speech.
To the Hebrews, it was a token that there would be no more universal floods.
And the second one is the in-flight recorded speech. This one's going to be noisy.
It was a token that there would be no more universal floods.
Okay, and the third one is the target speech recovered by the using the method we proposed in this research.
To the Hebrews, it was a token that there would be no more universal floods.
All right, and next one is the next one is the original method.
That there would be no more universal floods.
So the wave unit. And the next one is the you can consider this as the best method until now.
To the Hebrews, it was a token that there would be no more universal floods.
Yeah, this one is the intelligibility of it is pretty high, but you can see there's a slur in between of words. And the next one is the MWFGMM.
It was a token that there would be no more universal floods.
Yes. So we also compared the relative transfer function between the input mixer and the output enhancing signal. And apparently the deep learning based method achieve a higher, relatively better result in the Hamilton angle comparison, because smaller value indicate a better performance in the spatial cue preservation. And here we also do a ablation study on the performance of each step, each change we made on the from the original method. So as you can see, with each step we get an improvement, and the whole process is pretty stable. And we compared it with multiple other methods, like the baseline wave unit and the multi-channel conv-net, the MWFGMM. And as you can see, our method achieve a relatively higher performance, and it achieves a relatively similar performance as the multi-channel conv-net. But our method have only approximately half of the parameters as in multi-channel conv-net, which means that we can achieve the similar performance with less computational complexity. And yeah, that's basically it. Thank you.
I will just use maybe less than 3 minutes to quickly conclude this talk. First of all, thanks Yifei for the discussion about deep learning-based spatial enhancement. So overall, what we have done is we have discussed the main issue of this whole topic due to very strong ego noise, basically the drone noise. Then this kind of application of enhancing the speech signals from the drone-based recording is pretty challenging. And when the drone is hovering, that's what we are discussing so far, right? So every application, every experiment we have done so far is when the UAV is hovering. We can actually use both signal processing-based method or machine learning-based method to achieve the task, particularly within the signal to noise ratio very low, which is minus 15 to 30 dBs, right? That's like a very low signal to noise ratios. And in these applications, we can also see that deep learning based can further enhance the performance of the speech enhancement. And then, but of course, there are further things we can do on these applications. So what are the future works and directions? So first of all, at the moment in the group, we are actually having a couple of thesis projects working on similar kind of different directions. One direction is we want to develop a more complex acoustic sensing systems, basically the microphone array systems, and so that it can actually go with the drone, fly with the drone, and then do the processing on board, and then potentially do the cleaning on the fly. So that's like one potential direction. The other direction is if we want to achieve the overall speech enhancement or kind of cleaning stage on board, then we need to actually find out what's the good processing algorithms which can run real time, and also which are high efficiencies, right? So because the onboard, there's always a limited memories and then the resources. It's unlike your computers on the station, right? So then if that's the case, we need to figure out what's the best or what's the better solution for the processing algorithm to achieve this task. On the other side, since I have been working on the active noise control direction, I'm also keen to looking at whether there is any onboard system which potentially can achieve this real-time noise control, especially for the active noise control on the UAV. So therefore, we can actually achieve not only the quietness on the drone, like cleaning data on the drone, also potentially control the noise coming down to the ground. So whoever actually across the area which the UAV fly, it can actually achieve the quietness when you actually below the UAV. So if any of you have interest in any of this direction, feel free to contact me. Potentially we could collaborate. Thanks all for all the collaborators, the collaborator from ANU, also the collaborator here, Yifei. And if you have any questions with me or Yifei, feel free to ask. I think we have still a few minutes left for Q&A. Thanks all for today.
All right. Thank you, Aimee, Yifei, for that really exciting talk. I personally did enjoy it. Do you have any questions in the crowd? No?
I have a question. So you said that in the future you're looking more towards like onboard processing. Why has that not happened yet? What are the challenges which you're facing already that you haven't solved yet that means it's not able to like live process noise?
So first of all, if you have kind of understand what we discussed before, the discussion we had, the previous method we have proposed in this task, especially for the enhancement task, normally it's actually involve a lot of computation. So even for the signal processing method, because we are doing multi-channel signal processing, and also potentially if we want to enhance the signal, we actually need a lot of microphones, and that will also kind of bring more computations needed. And of course, with the deep learning method, there is also a need for like large computations. And that's one thing. The other thing is, if you want to have an onboard system do all these tasks, this onboard system need to have multiple functions. For example, it has to be wireless. It has to be able to communicate back with the station. And also it has to be light enough to connect with the UAVs and then fly with the UAVs. But there are a lot of constraints so far to make this happen. So I guess some of them, potentially their solution existed, but then all of them combined, there is still a need for further investigations.
Another question, sorry. Do you, with the machine learning side of it, do you go through a large training period where you look at what does the noise of this particular drone, like what's the noise usually look like? Therefore, if we know what it usually looks like, we can filter it out because we know that, as opposed to doing it live, you could possibly have a large data set of when it moves forward, it makes this noise. When it's hovering, it makes this noise, and then filter it out that way. Is that something that you guys have looked at?
Yifei, you. You want to?
So the machine learning based method is kind of like dependent on the data set. And if we train it with all the data set coming from the hovering stage, like the UAV is hovering there, then we can only, the model can only deal with the situation that the UAV is hovering there. So if we are using it for when the UAV is like doing different gestures, then the algorithm probably the performance will decrease or doesn't work at all. Could be possible. And so yeah, basically like that.
So it's more modular.
Yes. Yeah, so if we want to, if in the future we want to do like a wireless communication something, because that way you will be definitely doing different gestures in the sky. It won't be fixed on the floor, and perhaps we need to do some more data collections and to train the model, if that will happen. Yeah. No worries.
I mean, for that, the gesture stuff, I mean, if it's moving forward and backward, aren't the sound just like they add up together, kind of? So you only need to test out different directions. I don't know.
Yeah, the direction could be one problem, because if it's like moving forward and moving backward, the microphone will face in different directions, right? That could be one of the issue, and also the other issue is that because if it's moving forward or backward, the speed of the rotors could vary.
Yeah.
So it will make a different type of the noise. Then it could damage
But
the.
you can actually monitor the actual speed of the motor, right?
Yes, we can. That's actually one of the direction we are trying to do. We are trying to include the multimodal data set in it. Like we include not only the noise data, we can also include the speed of the rotors, so that we can like using it as a reference.
Amazing.
Thank you. Any other questions?
All right. That's all then. I think we might then put this to a close. Aimee, Yifei, you want to say anything else? Want to add on anything more?
I guess we just present like one application for this, basically making drone listen. Of course, if you have any interest in any of the things we bring up at the beginning, then feel free to contact us, and then we're always here to have discussions. Thank you. Thank you for your interest.
Yeah, we're not live anymore.